So next, the next thing that came along was something called SHA-1. SHA-1 is much more rigorous, and we'll look at the difference here. So we'll say OpenSSL, we'll use SHA-1. And that's quite a bit longer. So the MD5 hash was about 33 characters or so. SHA-1 will give us 41. That's a lot more entropy when you talk about cryptographic hashing. But again, you probably all got the same output as me. So again, you feel good implementing these things. You're like, oh, I hashed the passwords using SHA-1. But it's, again, I can create a rainbow table of all these things already very, very easily. And it stores well in memory. So we're going to use what is now currently the golden standard, which is SHA-256. And your output there is going to be the same as mine because we're all using the same password. We're all using the same hashing algorithm. However, it becomes a lot more difficult to implement a rainbow table when the sizes are so big. So MD5 was 33 characters. SHA-1 was 44. SHA-256 is 65 characters. That's pretty hard. Now we're getting into the randomness zone where it's much harder to crack or save all these passwords because it would just blow up your memory really quickly. But we're still not there yet. That's still not very secure. And this is just the common SHA-1 patterns for password, password, password 1, 2, 3. Again, this already exists. I didn't invent any of these things. There are people in the world that dedicate themselves to security and cracking security. So what we need is something called a salt. So the salt is randomness. It's just a random number or hash, or it doesn't really matter, that is completely unique to that particular process at the time. So we take the input, we take the salt, which is that random number, then we give it to SHA or any sort of hash function, and then we get what's called a salted hash. So now if we were to take that foo password, we give it some random number, doesn't really matter, and we pass through SHA-1, now that password's unrecognizable. You will never know what it is. And it didn't take that much more work. We're still using cryptographic hashing, but that bit of randomness means no one can ever create a rainbow table of all these things. Now, I'm spending a lot of time on hashing and cryptographic functions because this is where you see a lot of mistakes breaking down. You see companies that get hacked and they store their passwords in plain text. They don't hash any of them. Why? Like, why? I just demonstrated why you should do that, and I demonstrated that in 5 minutes, yet people still do it. People still use MD5 as hashing. So when you're creating a web application, you never store your password in plain text. I think most people know that, but you still see it. People say like, oh, I've hashed it using MD5. We just explain why that's not secure either, because people are bad at passwords. And you know what I've also seen? Well, I'll just MD5 it like 10 times. That way, like I'm hashing, and that's, totally secure. Computers can do that too, like really, really easily. And it takes very little processing power to guess that. The only secure solution is to have a strong cryptographic function that's long and hard to crack with a random salt stored for every single user. That way, even if someone cracked your password database, it's just gibberish because they don't know the salts. They can't reverse that cryptographic hash. I know, that's a lot on hashing, why it's important. It's kind of rolled today. But security is one of the most basic things that we fail on and we fail on and we fail on. And as increasingly as more of our infrastructure is built on top of these web applications and servers and processes, we have to remember security is the number one thing we care the most about. Yes, question?
What's the advantage of SHA-1 over MD5 if they both give the same output for the same input?
The same output for the same input.
Meaning they both essentially do the same thing.
So all hash functions will always give you the same output for the same input. It's a mathematical function. Why we use the salt is you can't reverse it. And that's what makes a cryptographic hash versus just a regular hash function. A regular hash function, you can reverse it if you know what the input was, or if you knew what hash function they use, essentially, you can reverse that and run it backwards. That's not true for every hash function, but MD5 is particularly pretty easy.
Where do we get the salt, or what is typically used for the salt?
It could be anything, math.random. math.random applied to a hash function, which will give you another hash. Combine those together, and you solve you run those against the hash function. That will give you something completely random, unguessable, unbreakable with modern technology, and it doesn't take that long to implement. What's important is don't do the thing. Don't roll your own security. Don't roll your own hash function. I should have started with that. Do not write your own hash function. It's easy to say like, oh, I'm going to bit shift this and do this and add in this magic number. And it seems like you're like, oh, how hard can it be, you know? And you have something that looks random, but it turns out this stuff is called really hard. I think it's, if I'm remembering right, it's called like elliptical curve cryptography. So what that means is generally given a hash function, if you run it enough times, you'll start seeing a curve of it looks random, but it's actually not, because all mathematical functions follow some sort of linear break. So I took an entire semester of hashing, or not hashing, but kind of thinking about elliptical curve, thinking about randomness, how difficult randomness. I took an entire course in my degree because randomness is actually a very, very hard problem. Humans aren't random, computers aren't random. It's all predictable. If you follow that curve long enough, you can figure out what the pattern is, and you can reverse it. 2 questions.
What about bcrypt?
Bcrypt? I want to say bcrypt uses, let's look it up. What hash does bcrypt use? Blowfish cipher. Yeah, Blowfish is pretty common. I'm trying to remember what bcrypt is used in, but SHA-256 is the main one I know most about. SHA-1UC. MD5 is useful, as someone pointed out earlier, for validating the contents of a file. So instead of saying like, hey Jem, I sent you an email, did you get it? I'm like, how do I know it's from you? Or how do I know what that file was? You can run MD5 on that, and that's going to give you a hash function that's about 33 characters or so. Doesn't matter how big the file is, MD5 is always going to collapse it down to a set of characters. And then you can say, here's the MD5 of that. I can validate it on my end, and that way I know that the file was not tampered with at all, which is pretty cool. Like, again, that's a really common use case of validating files and saying, like, what I sent you is what you got.
So picking up on that previous salt question, you mentioned like you could generate a salt with math.random, but you wouldn't want to do that every time because it has to be the same salt that's always used, so that when you're comparing a password in like when someone's logging in, it's salted the same way to compare against the hash. So you need to store the salt somewhere, correct?
Exactly. Yeah, you need to store the salt in the database or something so it knows what to hash against. But that database is usually encrypted, and usually itself is hashed in some form. So it's just layers and layers and layers. If someone really wants to get into your system and they've got root access, there's easier ways of getting passwords. They can just sniff them over the wire in this case. But yeah, you're right. You have to store the salt somewhere, otherwise you can't apply it later down the line. Oh, I had a really good thing on MD5. Yes, MD5 is still useful. You don't use it. It's not considered cryptographically secure. Again, we explain why. It's pretty easy to crack. I can create every possible combination using MD5. But it is good for validation of files over the wire. Sometimes you see on open source projects, things like that, they'll say, here's the file, here's the MD5 hash, and just compare it on your end too. So you run MD5 and you can validate the file is what they say it is. Security, or what's the right term for it? Security chain software? No, the actual word escapes me. But the idea of you need to secure every single step of your software from when you download it to when it's running on the server is really important. We hear people about hijacking NPM libraries, things like that. And you're saying like, hey, I'm installing LeftPad. Well, how do you know? How do you know I can just take that domain and I created my own version of LeftPad, which does the functionality, but also has this little other functionality that sniffs your traffic and sends it back to me. You don't know if I've tampered with the file, but if you use something like MD5, you know the file is here's what the author wrote, here's what I have on the other end. So there is something called, now we're getting into it a little bit, and if you space out for a minute, that's totally okay. We're gonna get, there's something called collisions, and something with MD5 that's pretty short at only 33 characters. It's possible to create a collision. So I can create an identical file, or I can create a file that's different from your file, but it hashed in such a way that it matches your MD5. Again, because MD5 is not very complex. With SHA-1, collisions are extremely rare. I don't know if it's ever happened. SHA-256, they're pretty much impossible. So again, there's pros and cons of everything. MD5 is pretty quick. SHA-256 takes longer, but one's more secure than the other. Jem, you spent a long time on hashing. You talked about some of the use cases. Where else do you see it? Cryptocurrencies. It's all about hashing. Bitcoin uses SHA-256. You solve a puzzle, you run the hash, you get a prize called a Bitcoin. We as humans decided that Bitcoins are worth something, hence the foundation of modern capitalism. Or in, what are we at? Post-capitalism? Is that the right term for where we are today? Doesn't matter. Ethereum uses something called Keccak 256. You may hear that referred to as SHA-3. We don't use SHA-3 because it's not considered cryptographically secure, but Ethereum uses a version of that. But don't say it's SHA-3 because the Ethereum people get annoyed. But that's really what Keccak is. Anybody heard of ransomware? I'm sure you've heard. What is ransomware?
Software that gets maliciously installed in a computer system that encrypts all the data on that system.
Yeah, and how does it encrypt all that data?
Hashing.
Yeah, exactly. So instead of taking your 100 gigabytes of files and try to put them in another directory and put a password around it, I'll just take all those files and run it through my hash function. And that way, I just have this giant block of text that represents all of your data, but you now can't get to it because I've deleted the original copy, and only I know the key to unlock it using my salt in the hash function. And that's what ransomware is, and that's why it's particularly malicious and it's not easy to crack. Because again, this is cryptographically secure hashing. You're not supposed to crack it. Ransomware is a blight. It will never go away. And if I can go on a rant here, there is a very strong correlation between the rise of ransomware and the rise of cryptocurrencies, because I can pay someone anonymously, hence where these things exist. But crypto is a very interesting, I don't know, it's pushing the bounds of what we know about, one, cryptography, two, distributed computing. Interesting topic, another day.